Hello everyone. Now we have to discuss numerical problems on single phase transformers. So we have completed total theoretical part of single phase transformers. It's time to discuss problems on single phase transformers. So first problem is a single phase transformer has 400 primary and 1000 secondary turns. The net cross sectional area of the core is 60 square centimeters. So if the primary winding be connected to a 50 hertz supply at 500 volts, then we have to calculate the peak value of flux density in the core and the net voltage induced in the secondary winding. So this is the problem based on EMF equation of a transformer. So now we have to discuss the solution. So he wants what? Magnetic flux density along with the voltage induced in the secondary winding. Voltage induced in the secondary winding. So first we have to write the given data. So primary induced EMF, that is E1 should be equals to V1, which is equals to what is the value? 500 volts. Clear? And then frequency, which is equals to what? 50 hertz. And what about primary turns? Those are nothing but N1 should be equals to what? 400. And secondary turns are what? 1000. And given that area of the core, which is equals to what? 60 centimeters square. So this is the given data. We have to calculate secondary EMF, that is B max is what, and E2, what is the value of E2? So we can calculate the E2 value should be equal to what? 4.44 phi NF. From that we can able to calculate the value of E2, or we can use the relation between number of turns and EMF, right? So before calculation, E2 by E1 should be equals to what? N2 by N1, and E1 should be equals to what? 4.44 phi N1F, like that. E2 should be equals to what? 4.44 phi N2F. Let us take phi M, maximum value of flux. So these are the equations. From this we can able to calculate E2, and phi is equals to what? Into area. So these are the required formulas to calculate the given data. Required formulas to calculate the required data. So from this given data we have to calculate the required data, that is BM and E2. Okay. So first we have to calculate maximum flux density, that is A, right? B max. So let us take this formula, 4.44 phi M N1 into F. This should be 4.44 phi M should be equals to what? Bm into A, N1 into F. So from this E1 is given as what? What is the value of E1? E1 should be 500, which is equals to 4.44 into Bm, we don't know. What is the value of area? That is 60 centimeters square. That is nothing but 60 into 10 power minus 4, right? Into what is the value of N1? N1 should be 400, and the given frequency is what? 50 hertz. So from this Bm should be equals to what? 500 by 4.44 into 60 into 10 power minus 4 into what is the value? Into 400 into Okay, from this we will get the value of B max should be equals to 0.9384 Tesla. Therefore Bm should be equals to what? 0.9384 Tesla. Just we have the formulas, just substitute these values into that. Okay, so this is the maximum flux density from the given data. Now we have to calculate voltage induced in secondary, right? Voltage induced secondary winding. So we all know that. What are the formulas for that? We can calculate E2 should be equals to what? 4.44 phi m into F. You can get the same value of magnitude, or you can calculate E2 by E1 should be equals to N2 by N1. So what is the value of E2? We don't know. So E2 should be, E1 is what? 500, N2 is what? 1000, and N1 is what? I think 400, right? So from this the value of E2 should be equals to what? E2 should be 2.5, 1250. E2 should be 1250, or from this also you can get 4.44 into phi m is nothing but what? We can get the phi m as 0.00563 webers into N2 are nothing but what? 1000 into F. From this also we can calculate the value of V2. Okay, this is the answer from this. So value of E2 induced in secondary winding from this method or by using this relation. You can use this relation or this relation. This is about the first problem based on EMF equation. So next, the no load current of a transformer is 5 amperes at 0.25 power factor. So this is the problem based on operation of transformer under no load condition. So the no load current is nothing but 5 amperes at, what is the power factor? That is no load power factor is what? 0.25 when supplied at 235 volts 50 hertz supply. So the number of turns on the primary winding is what? 200. N1 is 200, and calculate the maximum value of flux in the core and the core loss and the magnetizing current we have to calculate. So we all know that operation of transformer under no load, that is no load current I0 should be equals to what? 5 amperes, right? And cos phi naught should be equals to what given? 0.25, and primary induced EMF, that is E1, which is equals to V1, which is equals to what? 235 volts. You have to write no load current, no load power factor, primary induced voltage, like that you have to write. Okay, and the supply frequency, which is equal to what? 50 hertz. And yeah, N1 should be equals to, primary turn should be equals to 200. Okay, primary turn should be equals to 200. So we have to calculate the maximum flux density Bm, and this is given data. Okay, the required formulae. Okay, what are the required formulas? We have what? First we have to calculate maximum flux density from this EMF equation, right? 4.44 phi m N1F, which is equals to 4.44 B max into A N1 into F. Can we have area? So no area. So we have to calculate the flux only. We have to calculate the value of flux. He wants only the maximum flux. He needs only flux only. Okay, from this, wait. He wants only maximum flux in the transformer. So from this, phi m should be equals to what? E1 by 4.44 N1 into F, clear. And then core loss component, right? And then core loss. We all know that under no load condition, core loss should be equals to what? P naught should be equals to W naught should be equals to what? Supply voltage into I naught into cos phi naught, right? Then third one is what? Magnetizing component of current, that is I mu, which is equals to Im should be equals to I naught into sin phi naught. So these are the required data from the given data we have to calculate. So first we have to calculate phi m. Okay, first to read the question and what is the given data and what is the required data. So to get the required data, first you have to recollect what are the required formulas to get the required answers. Then only you will get the correct answer. This is the systematic way of approach for calculation of a problem. The first, phi max. So what is the formula? Phi max should be equals to what? E1 by 4.44 into number of primary turns into F, which is equals to what? What is the EMF given data? 235 by, this is 4.44 into N1 is what? N1 is given, N1 is 200 and frequency is 50. From this you will get 5.293 milliweber. The answer is what? 5.293 milliweber. And second one, which is what? Core loss, that is P naught, which is equals to what? V1 I naught cos phi naught. What is the value of supply voltage? That is 235 into I naught is what? 5 amperes and power factor is what? 0.25. What is the answer now? From this you will get 293.75 watts. This is about core loss component. And what is third one? I mu, which is equals to what? Magnetizing component of current, which is equals to I naught into sin phi naught. So given sin phi naught, you will get I naught is what? 5 into square root of 1 minus cos phi naught whole square, right? Which is equals to 5 into 1 minus cos phi naught is what? 0.25 whole square. From this you will get 4.84 amperes. So this is the, so first we have to calculate phi m, then core loss component, then magnetizing component of current. This is about operation of transformer under no load condition. So the next problem is a single phase transformer with a ratio of 440 by 110 volts takes a no load current of 5 amperes at 0.2 power factor lagging. Okay, no load operation data, and if the secondary supplies a current of 120 amperes, here you have to underline this word. What is that statement? If the secondary supplies a current of 120 amperes at a power factor of 0.8 lagging, means we have a load across secondary, then only we have a secondary current of 120 amperes with a power factor of 0.8 lagging, and that load is what? Lagging load, and the load is what? Lagging load only. So the estimate the current taken by the primary, that is we have to calculate I1. So a single transformer with a ratio of 440 by 110 volts takes a no load current of 5 amperes at 0.2 power factor lagging. So if the secondary supplies a current of 120 amperes at a power factor of 0.8 lagging, so estimate the current taken by the primary. So this is the problem based on operation of transformer under load condition. Okay, so this is what? By default this is E1 by E2, or you can get the voltage HV winding voltage is nothing but what? 440. LV winding voltage is what? 110 volts. Or if he didn't mention regarding that point, just you have to take E1 by E2 by default. Okay, any ratio, if he given like this, some value by some value, it should be treated as E1 by E2. Okay, solution. First we have to write the given data. Okay, just read the problem once again. And given E1 should be equals to what? 440 volts, clear. And E2 should be equals to what? Secondary EMF 110 volts. And given then I0, no load current 5 amperes. You have to write that primary induced EMF E1, secondary induced EMF, no load current I0, like that you have to write in the exam. And no load power factor cos phi naught should be equals to 0.2 lagging. And then given the secondary supplies a current of 120, means what is that? I2, right? That is 120 amperes. And what is the power factor? Secondary power factor, that is cos phi 2, which is equals to what? 0.8 lagging only. And we have to calculate the value of I1, right? I1. So the required formulae. First, any problem, first read the problem and write down the given data. Later, what is the required data we have? That is I1, we have to calculate the value of I1 only. So in order to calculate I1 should be equals to what? We all know that I0 plus I1 double dash. So I1 double dash is nothing but what? Already I1 value, I0 value is given. So I0 plus I1 double dash is nothing but what? K into I2, right? Since I1 dash should be equals to I2 into K. So first we have to calculate K. What is K? E2 by E1, clear. So after calculation of K, and what is the secondary compensating power factor? Phi 1 dash should be equals to phi 2, right? This is the phase angle of this I1 dash. This is compensating current, load component of primary current. This is the flux of load component of primary current, which is equals to what? Secondary flux. These two are nullify with each other. So first we have to calculate I1. To calculate I1 we need K, then we need power factor, right? Okay. Right. Okay, let's calculate. First we have to calculate load component of primary current, this I1 dash, which is equals to what? K into I2, which is equals to what? What is the value of K? Which is nothing but E2 by E1 into I2. What is the value of E2? E2 is given as what? 110 by 440 into what is secondary current? 120, which is equals to what? 1 by 4 into 120, which is equals to what? 30 amperes. So I1 dash is nothing but what? 30 amperes. And this is lagging behind the applied voltage by I1 dash is lagging behind the applied voltage by what? Phi 1 dash, right? Lagging behind the by Phi 1 dash. So what is the phasor diagram? flux I mu, this is V1, this is IW, this is I naught, right? This is E2, which is equals to V2, this is E1. Here the load is what? Lagging load. So let us take this I2, this is phi 2, right? This is what? I1 double dash. From this is what? Phi 1 dash, right? See, lagging behind the applied voltage by phi 1 dash, right? That's why we have written this. And what is the resultant between these two? And the resultant is what? I1. That's it. We have to calculate this I1. This is what? Phi 1. And this is what? Phi naught. Clear? This is the phasor diagram under lagging load. Okay, that's why you have written this statement, lagging behind the applied voltage by phi 1 dash. Now, what is phi 1 dash? Which is equals to phi 2 only, because the phase angle of load component of primary flux should be equals to phase angle of load component of secondary flux, which is equals to what? Cos inverse secondary flux given as what? 0.8, which is equals to what? 36.87 degrees. Clear? Therefore, no load current is given as what? I naught should be equals to 5 amperes. This is lagging behind the applied voltage by what? Phi naught. Therefore, phi naught should be equals to what? Cos inverse 0.2, which is equals to what? 78.46. You can write that point. I naught is lagging behind V1 by phi naught. Clear? Therefore, I1 should be equals to I1 dash plus I naught. How can we calculate this? Simply I1 dash should be equals to what? I1 dash cos phi naught plus I1 dash j I1 dash sin phi naught. Like that, plus I naught cos phi naught plus j I naught sin phi naught. Then substitute the values. You will get I1 dash cos phi 1 dash, sorry, this is phi 1 dash, phi 1 dash. Clear? So I1 dash cos phi 1 dash, which is equals to what? 30 into 0.8. Like that, j I1 dash 30 into sin phi naught. If it is cos phi naught is 0.8, sin phi naught should be equals to 0.6. Clear? Plus what is I naught? 5 into 0.2 plus j into 5 into, if it is 0.2, this is 0.98. So from this we are going to get the answer is what? 25 plus j 22.9 amperes. This is what? I1, primary current. So primary current is what? 25 plus j 22.9. So what is the magnitude of I1? Which is equals to 25 whole square 22.9 whole square. Therefore, the primary current should be equals to what? 33.9 amperes. So finally, the primary current is what? 33.9 amperes. Therefore, phase angle phi 1 should be equals to what? Phi 1 should be equals to what? Tan inverse from this. What is the phase angle? Phi 1. Tan inverse 22.9 by 25. Simple problem. Therefore, phi 1 should be equals to what? 42.5, which is what? Lagging supply voltage by 42.5 degrees. This is what? 42.5 degrees. Like that, you have to calculate the given problem, right? Next, this is the problem. A 50 kVA 4400 by 220 volts transformer has 3.45 ohms and 0.09 ohms, which is what R1 R2. Like that, reactance is what 5.2 ohms and 0.015 ohms. Calculate the equivalent resistance referred to primary, referred to secondary, and equivalent resistance referred to primary, referred to secondary. Like that, equivalent impedance referred to primary, referred to secondary, and total copper losses. So from the given data, we have to calculate total calculations. Given data, what is the data? So K, which is equals to what? Which is equals to what? E2 by E1. What is the value of E2? That is 220 by 4400. What is the value? 1 by 20 is nothing but transformation ratio. And full load secondary current we have to calculate, right? Full load secondary current I2 should be equals to what? KVA rating of transformer, that is 50 into 10 cube by E2 is nothing but what? 220. What is the answer? 227.3. Or directly we can calculate. This is not given data. Next, I1 we have to calculate. Okay, you can calculate 50 into 10 cube by 4400. Okay, or you can calculate, which is equals to K into I2, or you can calculate like this or like this, which is equals to what? 1 by 20 into 227.3, or you can get like this, right? Sorry, this is 50 into 10 cube by 4400. What is the value of I1? KVA rating of transformer by obviously E1, right? Okay, in any case you will get the value of I1 as 11.36 amperes. Clear? I1 is 227.3, sorry, I2 is 227.3, I1 is 11.36, and K is what? 1 by 20. So we all know that R1 is given, R2 is given, X1 is given, X2 is given. Therefore, equivalent resistance, first bit is equivalent resistance referred to primary, right? First we have to calculate the equivalent resistance referred to primary. Equivalent resistance referred to primary, first bit, equivalent resistance referred to primary. That is what? We all know that R01, right? That is R1 plus R2 dash, which is equals to what? R1 plus R2 by K square. So which is equals to, what is the value of R1? 3.45 given like that, and R2 is what? R2 is given as what? 0.009 by K square, that is 1 by 20 whole square, which is equals to 7.05 ohms. This is the equivalent resistance referred to primary. Like that, referred to secondary, that is R02, which is equals to what? R2 plus R1 dash, that is R2 R1 into K square. What is the value of R2? R2 is nothing but 0.009 plus K square into R1. R1 is given like that into 3.45. Direct formula you have to substitute in that formula only, you will get the answer 7625 ohm. Next we have to calculate reactance referred to primary. Reactance referred to primary, that is X01, right? that is x1 plus x2 dash, which is equals to what? x1 plus x2 by k square, which is equals to, what is the value of x1? 5.2, and x2 is given as 0.015 by k square, 1 by 20 whole square, which is equals to what? 11.2 ohms. And the equivalent reactance referred to secondary. If it is referred to secondary, what is the formula? x02 should be equals to x2 plus x1 dash. So we all know that what is the value of x2 plus, which is x1 into k square. x2 is what? 0.015 plus 5.2 into 1 by 20 whole square. What is the value of x02? That is 0.028 ohms. So these are from A, B, C, D. Referred to primary, secondary resistance, like that referred to primary, secondary reactance. Next we have to calculate equivalent impedance referred to primary, that is E. Right? That is Z01, which is equals to what? R01 plus JX01. So we all know that what is the value of R01? 7.05 plus J into 11.2. So from this we are going to get, which is equals to 13.23 at an angle 57.81 ohms. Okay, like that F, equivalent impedance referred to secondary, that is J, let us say Z02, that is R02 plus JX02. Simple formulas, right? So we will get 0.017625 plus 0.028, which is equals to what? 0.0331 at an angle 57.81 ohms. So F. Finally we have to calculate the copper loss content. A, B, C, D, F, G. Next G is nothing but copper loss, right? We all know that before transferring, after transferring, the copper loss content is same, right? That is PCU, which is equals to I1 square R1 I2 square. That's why in the before itself I have calculated the value of I1 I2, which is equals to what? I1 square R01, which is equals to I2 square R02. At any case, just we have to substitute the value of I1 here and substitute the value of R1 here, or you can calculate from this two, I1 square into R01. From this you will get the value of PCU as 910.4 watts. Just you have to cross check the answer. Like that you have to calculate the equivalent resistance referred to primary, secondary, equivalent reactance referred to primary, secondary, like that equivalent impedance referred to primary, referred to secondary. Finally the total copper loss content before transferring, after transferring referred to primary, after transferring referred to secondary, all are equal. Next problem, fifth one. A 220 volts what is the problem? A 220 volt 60 hertz single phase transformer has a hysteresis loss of 340 watts, right? 340 watts, and eddy current loss of 120 watts. If the transformer is operated from 200 volts 50 hertz supply, means calculate the total iron loss component in the transformer. This is the problem based on losses. Very important problems. We have very most important problems on losses. First we have to calculate the iron loss component. Given V1 which is equals to 220 volts, F1 which is equals to 60 Hz. At this stage, what is WH which is equals to 340, and WE should be equals to what? 120 watts. Like that you have to write. Later, what is the value of voltage? 200 volts, and Ft equals to what? 50 hertz. In that case, we have to calculate finally iron loss content, right? What? So from this, what is the value of iron loss component? Which is equals to plus, sorry, eddy current loss, which is equals to what? 340 plus 120, which is equals to what? 460 watts, right? So first we have to cross check V1 by F1, which is equals to V2 by F2, which is equals to constant. Therefore, what is V1 by F1? 220 by 60, which is equals to what? Which is less than 4, right? First. Second, what is V2? V2 by F2, which is equals to, here we can write V1 by F1. V2 by F2 is what? 200 by 50, which is equals to 4. So, therefore, 1 is not equals to 2. From this, what is the condition? V by F is not constant. So, we have obtained V by F is not constant, right? Therefore, what is that? P max, which is equals to not constant. Obviously, this is comes under second case. Therefore, for that, iron loss component should be equals to plus this, right? So, to calculate iron loss, what is hysteresis component we have to write? So, we can write, okay. First, we have to write like this. In that, WH is proportional to what? Supply voltage power 1 by F power 0.6, and eddy current loss is proportional to only supply voltage square, right? Therefore, by, or like that you have to write V2 by V1 power 1.6 and F1 by F2 power F1 by F2 power, you can write 0.6. Okay. So from this we have to calculate WH2. What is the answer? WH1 into V2 by V1 power 1.6 and F1 by F2 power 0.6, right? So from this, which is equals to V1 by V2 whole square. From this, the required WE2 should be equals to what? WE1 into V1 by V2 whole square. So this is 1, this is 2. So from this, what is WI, which is equals to WH1 into, that is 340, right? WH1 is 340 into V2 is what? 200, which is equals to 220 power 1.6, and F1 is given as what? F1 is 60. This is 60 by 50 power 0.6 plus 120 into 200 by 220 whole square. So from this, the value of iron loss component should be equals to 425 watts. This is the iron loss component for the case. So like this we have to calculate, right? Just we have to cross check the ratio between voltage and supply. So V by F is not constant. Therefore, WH is proportional to like this, W proportional to V square. Next problem. A transformer has iron loss of 90 watts at 60 Hz 52 watts at 40 hertz. Both losses are being measured at same flux density, that is B max is constant. He provided B max is constant, that is case 1. Calculate the total iron loss in the transformer at 50 hertz. We all know that if B max is constant, obviously whether it is hysteresis loss or eddy current loss, both are proportional to frequency only, right? Wi should be equals to what? 90 watts at 60 hertz. Later Wi, which is equals to what? 52 watts. What is the frequency? 40 hertz. Given Vm, which is equals to constant. Here magnetic flux density is constant, therefore iron loss, or first we have to hysteresis loss is proportional to frequency and eddy current loss is proportional to frequency square, right? Because B max is constant. So from this, iron loss should be equals to AF plus BF square, which can be written as AF, this can be written as BF scale. First we have to calculate the values of A and B. Later we have to calculate the iron loss component at, calculate the total iron loss at 50 hertz. Later we have to calculate the value of iron loss component at 50 hertz. So for this 90 at 60 hertz, right? Therefore 90 watts at A into 60 plus B we don't know at 60 square, like that 52. So from this, first we have to take, we have iron loss component of 90 watts at 60 hertz. So from this equation we have to write that. Later iron loss component of 52 watts at frequency of 40 hertz. Again A into 40 hertz plus B into 40 whole square. So by solving these two equations, above two equations, A should be obtained as 0.9 and B should be equals to 0.01. Therefore, what is the required iron loss component equals to what at F is equals to 50 hertz. So for this we have to calculate the iron loss component at 50 hertz. That is, iron loss component should be equals to AF plus BF square, right? What is the value of A? 0.9 into what is the frequency? 50. What is the B? 0.01 into 50 whole square. So from this, this is 45 and this is obtained as 25. So the total iron loss component is 70 watts, which is at 50 hertz. So at 60 hertz we have 90 watts, at 50 hertz we have 70 watts, at 40 hertz we have 52 watts. With the reduction in frequency, the iron loss component is decreases, right? That is, at 60 hertz iron loss should be equals to what? 90 watts. At 50 hertz, what is the value of iron loss, which is equals to obtained as 70, right? Like at 40 hertz, which is obtained as, what is the value? 52 watts. So what is the relation? Frequency decreases if frequency decreases, iron loss component decreases. What is the reason? Since B max, which is equals to constant, that is iron loss or hysteresis is proportional to F and eddy current proportional to F square. That's why if frequency decreases, iron loss component decreases. Okay. Next problem. Next is what? Yeah. A single phase transformer on open circuit condition gave the following test results, and these are the applied voltage 192 volts and 288 volts. Frequency is what, 40 hertz, 60 hertz, and power drawn is what, 39.2 watts and 73.2 watts. Okay, these are the obtained results for different supply voltages. For one instant we have to provide 192 volts, and second instance we have to provide 288 volts, and the assumed Steinmetz coefficient is what, 1.6 for steel. Find out the hysteresis and eddy current losses separately if the transformer is supplied with 240 hertz and 50 hertz. So at any case we have to satisfy the case what, V by F is constant. So this is the case 1, this is case 2. So we have to calculate the iron loss component, which is nothing but what, WH and WE at this case 3. This is case 3, right? So first we have to calculate the constants of A and B. Later we have to calculate at this, this is voltage, right? This is supplied with 240 volts, this is not hertz, 240 volts and 50 hertz. Okay, simple problem. So given that V1 which is equals to what, 192 volts, and F1 which is equals to what, 40 hertz, like that V2 which is equals to what, 288 volts, and F2 which is equals to what, F2 is 60 hertz. Okay, then what is V1 by F1, which is equals to 192 by 40, which is equals to 4.8. okay, 4.8, like that, and P2 by F2 which is equals to what, 288 by 60. Obviously we are going to get 4.8. Therefore V1 by F1 which is equals to V2 by F2 which is equals to constant, which is equals to B max, right? B max is constant. Therefore what is the relation? Therefore iron loss component which is equals to A into F plus B into F square. So from the first case, what is the iron loss component? 39.2. From the second case, what is the iron loss component? 73.2. What is the frequency? At 40 hertz we have 39.2, at 60 hertz we have 73.2. Then substitute these data into this equation. So we have 39.2 watts at what? At 40 hertz, right? That's why A into 40, B into 40 hertz. Next we have 73.2 watts of iron loss component at 60 hertz of frequency. That's why 60 square. So by solving 1 and 2, what are the values of A and B? A should be equals to 0.5 and B should be equals to 0.012. Therefore we have to calculate first, what is the answer? This for case 3 we have to calculate the eddy current loss and hysteresis loss, right? So but what is the, this is the total component of iron loss, this is total component of iron loss at 40 and 60 hertz, but he needs hysteresis and eddy current loss separately. Therefore with the 40 hertz of frequency, what is the WH and WE? With the 60 hertz of frequency, what is the WH and WE? We have to calculate. Therefore for that, at 192 volts 40 hertz we have to calculate WH, right, which is equals to what? A into F only. What is the value of F? A into 0.5 into F is what? 40, which is equals to what? 20 watts. Like that, W should be equals to what? B into F square. What is the value of B? 0.012 into 40 square, which is equals to what? 19.2 watts. So these are the hysteresis and eddy current losses at 40 hertz. Therefore we have to calculate the component of WH and WE at 240 and 50 hertz. right? Therefore, at 240 volts, 50 hertz, what is the value of WH? WH should be equals to what? Before that, what is V3 by F3? From this is V3 by F. First we have to satisfy the condition, that is 240 by 50, which is equals to what? 4.8. Therefore, V by F, which is equals to constant, that is V1 by F1, which is equals to V2 by F2. This is V3 F3. Then only WH, which is equals to what? WH is equals to what? Is the red color? WH is equals to what? Proportional to frequency, and then only eddy current loss is proportional to F square. Therefore, from this, which is equals to F1 by F2, and WE1 by WE2 should be equals to F1 by F2 whole square. So from this we need WH2, that is H1 into F2 by F1, and from this WE2 equals to WE1 into F2 by F1 whole square. So what is the value here? WH1 is nothing but 20, right? What is the frequency? F250. These 20 watts at F1 only, that's why 40. What is the answer? 1.25 into simply 25 watts, right? Like that, from this, which is equals to WE1 watt, which is equals to 19.2 into F250, this is 40, which is equals to what? You can get 1.25 whole square, approximately we will get 25 watts only, right? Approximately this is equals to 20 into 1.25 whole square, you will get the approximate 30. Approximately you will get 30 watts. Just you have to substitute the values in this. You can consider F1 value as 40. This is the value of WH1 at 40 only. That's why if F1 is 40, WH1 is 20. Or if you consider F1 as 60, you have to calculate the hysteresis and eddy current loss at F1 60 Hz. Like that, you have to calculate hysteresis and eddy current losses for different cases. So this is the problem. A 10 kVA 200 by 400 volts 58 single phase transformer gave the following test results. OC test, that is which is conducted on LV, right? SC test, which is conducted on HV. LV winding is short circuited, and the data is what? 200 volts, 1.3 amperes, 120 watts are nothing but what? These are nothing but iron loss components. These are nothing but copper loss component. Therefore, find parameters of equivalent circuit as referred to LV winding. So we have to calculate this data. The solution for this problem is, so these are the results from open circuit test and SC test, right? So this is the supply voltage, this is no load current because there is no load across secondary, and this is iron loss component, this is copper loss component, and this is rated current, and this is the supply voltage, that is 5% of rated voltage is applied. And find, we have to calculate the equivalent circuit parameters referred to LV winding. So with respect to 200 volts, we have to calculate the equivalent circuit parameters, that is R01 referred to primary. Okay, so here E1 is nothing but 200, that is LV winding voltage. So referred to LV side, we have to calculate the parameters. Therefore, given that I0 is what? 1.3. Finally, P0, which is equals to what? 120 watts. Later, supply voltage, which is equals to what? V0 should be equals to 200. And we know that how to calculate cos phi naught, which is equals to no load losses by P1 into I naught, which is equals to what? 120 by 1.3 into 200. What is the answer? You can get, right? This is lagging. Clear? Therefore, energy component of no load, that is magnetizing component, that is working component of current, which is equals to I naught into cos phi. Simple, we have to calculate R naught, X naught, IW, I mu and all data which is referred to LV winding, right? I naught is what? 1.3, power factor is 4615, which is equals to 0.6 amperes. Therefore, later mu should be equals to what? I naught into sin phi, which is equals to I naught into square root of 1 minus cos phi naught whole square. After substituting this, we will get 1.1533 amperes. This is about magnetizing component of current. Later we have to calculate R naught, that is, right, R naught should be equals to what? Supply voltage by IW, which is equals to what? 200 by 0.6. What is the answer? 333.3 ohms. Therefore, X naught should be equals to what? B1 by I mu, which is equals to 200 by 1.1533, which is equals to 173.42 ohms. Later we have to calculate equivalent impedance referred to HV side Z02, which is equals to, what is the data? Load side, right? This voltage by this current, that is VSC by ISC. What is the answer? 22 by 30, which is 0.733 ohms. And then equivalent resistance R02, copper loss contained by ISC whole square, right? 200 by ISC is nothing but 30 whole square. We will get 0.22. Just only if you know the formula, you will get the answer. These are the formulas to calculate the parameters. Therefore, after getting X02, R02, you will get X02, which is equals to what? Square root of Z02 whole square minus R02 whole square, which is equals to 0.733 whole square minus 0.222 whole square, which is equals to 0.7 ohms. So, next, what is the transformation ratio, which is equals to what? E2 by E1, which is equals to what? 400 by 200, which is equals to 2. Therefore, equivalent resistance referred to LV winding, which is equals to R01, which is equals to R02 by K square. You can calculate by calculating R02 by K square, or you can calculate R1 plus R2 dash, which is equals to R1 plus R2 by K square also, if you know the value of R2. Okay, but we have the value of R02. From this, R01 should be equals to what? 0.222 by K square is what? 2 square, which is equals to 0.0555 ohms. Like that, equivalent resistance referred to, reactance to LV winding, which is equals to X01, right, which is equals to X02 by K square. From this, X01 should be equals to 0.7 by 4, which is equals to 0.175 ohms. So, like that, you have to calculate equivalent resistance referred to LV or HV. So, whatever may be the given required data, you have to calculate through the formulas. Next problem, a 58 single phase transformer draws a short circuit current of 35 amperes, 0.25 power factor lag when connected to 16 volts 16 volts 50 hertz supply. What will be the power factor if it is energized from 16 volts 75 hertz supply? Okay, so short circuit test is performed two times here. So first test is 35 amperes of current and 0.5 power factor lag, and in the second case we are having what connected 16 volts 50 hertz supply. What will be the power factor if it is energized from 16 volts 75 hertz source? So for this, let's see test 1. What is the data? It is 16 volts 50 hertz and cos phi SC should be equals to what? 0.25 lag, and ISC is what? And ISC which is equals to 35 amperes. Like that, short circuit test 2. From this test we have 16 volts 50 hertz, sorry 75 hertz, right? 16 volts 75 hertz. Then what is cos phi SC, right? We have to calculate the cos phi SC. So we all know that from SC test 1, Z01 in ohms is nothing but what? VSC by ISC, 16 by 35 which is equals to 0.457 ohms. Therefore R01 should be equals to what? Cos phi SC into Z01, right? Cos phi is nothing but what? R by Z. So cos phi SC is what? 0.25 into 0.457 which is equals to 0.114 ohms. So you all know that what is the reason to get less power factor under SC test? Because the frequency is reduced, that's why we are going to get the, because there is a change in the frequency, that's why we are going to get the change in power factor. We all know the observations. We have provided I rated and F rated, but we are going to get the variations in power factor with the variation in the supply frequency, right? That's why we are going to get the less than 0.5 power factor of short circuit test. Okay, and from this 0.114 ohms as R01. So what is X01, which is equals to Z01 square minus R01 square. From this you will get the answer as 0.43 ohms. So we have Z01, R01, X01. So from SC test 2, so X01, we have to calculate the new value of X01, that is X01 old into frequency F new by F old. What is X01 old? That is 0.43. F new is what? 75. F old is what? 50. So from this you will get 0.645 ohms. Therefore Z02 which is equals to R01 square plus X01 square which is equals to 0.654 ohms. Therefore we have to calculate cos phi SC under this condition, right? That is this R0 R by Z, right? 0.114, sorry, this is X01 new, X01 new, 0.114 by X01 new is what? 0.654 which is equals to 0.17 lag. Then the new power factor is what? 0.17 lag. If we see what is the observation here, if we increase the frequency from 50 Hz to 75 Hz, what is the observation of power factor? 0.17 lag. That is if F less than F rated, cos phi SC increases, or if F more than F rated, cos phi SC decreases. See, so based on this example you will have the clear cut idea, right? Next problem, a 20 kVA single phase transformer has efficiency of 98% at full load and half load. So this is the problem based on efficiency. The power factor is unity in both the cases, and calculate the efficiency of transformer at 3/4 of full load at UPF, right? Let's go through these problems. 20 kVA transformer, and the efficiency is same at full load and at half full load also, right, which is equals to what? 98%, which is equals to 0.98, and the power factor is unity, that is we are going to get unity. That is, what is the condition here? When the power factor is unity, this is what? Maximum efficiency, right? This is the condition to get maximum efficiency. When we have unity power factor, obviously the efficiency is maximum, right? Efficiency is maximum. So from this we can get the different values. Calculate the efficiency of transformer at 3/4 of full load, 3/4 of full load. So we all know that what is the formula for efficiency? At x of full load should be equals to x into E2I2 cos phi 2 by x into E2I2 cos phi 2 plus this is square into PCU plus PI, right? This is the formula to calculate the efficiency of a transformer. Here at full load and half load, 0.98 is the efficiency, and we have to calculate the efficiency at 3/4 of full load. That is, for full load x which is equals to 1, right? Like that for half full load, what is the value of x, which is equals to 1/2. Therefore for 3/4 of full load, x which is equals to what? 3/4. So we have a data efficiency for this which is equals to 0.98. For this also efficiency is nothing but 0.98. Then we have to calculate the efficiency for this 3/4. So we have to substitute the data into this, we have to calculate the values of efficiency first, later we have to calculate the value of efficiency at 3/4 of full load. Therefore 20 kVA is nothing but E2I2. So E2I2 is given as what? 20 kVA, and power factor is given as what? UPF. X is given as what? First case is what? Full load condition. Second case is what? Half load condition. Clear, right? And is there any information for PI and PCU? No. Now we have to calculate the values of PI and PCU. Clear? Therefore efficiency at full load condition, which is equals to, what is the E2I2? That is x value should be equals to 1, right? X which is equals to 1 into E2I2 given as 20 kVA into power factor is what? 1. That is x E2I2 cos phi by x into E2I2 cos phi plus x value should be equals to what? 1. That is 1 square into PCU. We don't know PCU, like that PI. So like that we have to get the equation. From this 20 by 20 plus PCU plus PI. But given that the efficiency at full load is nothing but what? 0.98. So from this we will get the equation Wi plus RPI WCU, right, which is equal to, after calculation we will get 0.408 kilowatts. This is equation 1. Like that we have to calculate efficiency at half full load, which is equals to, x value is now 1/2, given E2I2 20, power factor is 1 by half full load 20 into 1 plus x square 1/2 whole square, PCU we don't know, and PI which is equals to what? 20 by 10 plus PCU by 4 plus PI, which is equals to same, right, given that 0.98. So from this, what is the data? From this, the data should be equals to which is equals to WI plus 1 by 4 WCU, which is equals to PCU 0.204 kilowatts. So from 1 and 2 we have to get the values of W and WCU, right? Therefore from 1 and 2 WI should be equals to what? You will get 0.272 kilowatts and WCU should be equals to what? 0.136 kilowatts. And now we have to calculate the efficiency at 3 by 4 of full load should be equals to what? X is 3 by 4, that is 3 by 4 into E2 I2 is what? 20, power factor is what? 1 by 3 by 4 into 20 into 1 plus what is the value of X? 3 by 4 whole square into what is the component of copper loss? That is 0.136 plus Pi should be equals to what? 0.272. From this you will get the efficiency at 3 by 4 is nothing but 98.1%. So like this you have to calculate the required efficiency at different fractions of full load. Next, a 25 kVA 58 single phase, this is the range distribution transformer, has the following parameters: total series impedance like this, and total shunt conductance like this, and shunt susceptance is like this. Conductance is nothing but what? Z naught, which is equals to what? 1 by R naught. Susceptance is nothing but what? B naught, which is equals to what? 1 by X naught, right? Now we have to calculate the maximum efficiency of a transformer. At what fractions of X? We have to calculate X. At what fractions of X we are going to get the maximum efficiency? We all know that X should be calculated. What is the formula to get the fraction of X to get maximum efficiency? The fraction of X corresponding to maximum efficiency, which is equals to what? We can write that. We have a formula that is fraction of X corresponding to efficiency max, right, which is equals to Pi by PCU. We have a formula like this, square root of Pi by PCU, that's it. So given that first I would like to draw equivalent circuit. We have R01, X01, and we have a load. This is the load, that is 0.1 plus J1 ohms. Okay, this is 0.1, sorry, this is say 1.0. Load is not given, so there is no bother. Okay, and given that the supply voltage is 240, right, and this is given as 0.012 mhos, 0.012 mhos. This is what? 0.09 mhos. Clear? Okay, this is R01, X01. Now we have to calculate the maximum efficiency occurs at fraction of load, that is X component corresponding to maximum efficiency, that is Pi by PCU. Just we have to calculate P iron loss component and copper loss component. Later we have to calculate the value of X, that's it. First you have to calculate iron loss component, later copper loss component, then X, right? So we all know that given data, iron loss which is equals to what? P naught which is equals to Pi which is equals to V1 into I naught cos phi naught, which is equals to what? V1 into I naught cos phi naught is nothing but what? Working component of current, that is supply voltage V1. Working component current should be equals to what? Supply voltage by R naught, that is supply voltage square by R naught, which is equals to supply voltage square into Z naught. What is the reason? Since 1 by R naught should be equals to conductance. So supply voltage is what? 240 whole square into Z naught is what? 0.012, that is iron loss component is what? 691.2 watts. Clear? This is iron loss content. Therefore copper loss content should be equals to what? I1 square into R01, right? So what is the value of I1 square? I1 should be equals to what? Rated current. Just first you have to know the fraction of load, that is what? Square root of Pi by PCU. Then you have to calculate the value of Pi. Later you have to calculate the value of PCU. Then substitute in the formula, that is I1 rated should be equals to what? 25 into 25 kVA by 240, which is equals to what? 104.16 amperes. Therefore PCU should be equals to what? 104.16 whole square into R01, which is nothing but what? Given that 0.1, right? R01 is what? 0.1. From this 1084.9 watts of copper loss content and Pi of 691. Then we have to calculate fraction of load, that is fraction of load, that is X. Fraction of load corresponding to maximum efficiency is, which is equals to, what is the formula? Pi by PCU, right? What is the answer? Pi is nothing but what? 691.2 by PCU is what? 1085.1085, right? 0, let us say. So 0.798, that is X is 78.9% of full load, that is the meaning. So we are going to get the efficiency is maximum at 79.8% of full load, that is the meaning, right? Next problem. The following data were obtained from testing 48 kVA, 4800, 240 volts, 58 transformer. At what kVA the transformer should be operated for maximum efficiency? So in the last problem we have given the data regarding at what fraction of load we are going to get the maximum efficiency, but this is the problem regarding to get the value of kVA to get the maximum efficiency. So also calculate the value of maximum efficiency. We have to calculate the at what kVA of full load we are going to get the maximum efficiency. Like that we have to calculate the value of maximum efficiency at 0.8 power factor. So what is the formula to calculate load kVA corresponding to maximum efficiency, right? It is load kVA corresponding to efficiency max, which is equals to what? Full load kVA into square root of Pi by PCU, right? Full load kVA into Pi by PCU. Just we have to know the full load kVA is nothing but what? 48 into 10 cube. Just we have to calculate Pi by PCU, right? All data is given, that is Pi should be equals to what? 120. 600 is nothing but what? PCU. That's it. Square root of 120 by 600 is nothing but what? Fraction of X corresponding to maximum efficiency. Therefore what is this answer? Should be equals to full load kVA is nothing but what? Full load kVA, which is equals to sorry, which is equals to 48, right? into, or you can, in terms of kVA you have to write, that's why there is no term of into 10 cube. 48 into, what is pi? 120 by 600. What is the answer? 48 into 1 by root 5, which is equals to 21.467 kVA. Okay, therefore we have to calculate the efficiency, maximum efficiency. At this value of load kVA, we are going to get the maximum efficiency, right? Then we have to calculate the value of efficiency at 0.8 power factor lag. So efficiency, that is maximum efficiency at what? At which kVA? This much kVA, 21.467. That is, x is what? Full load. X is what? Sorry, first we have to calculate the value of x, right? So first this is the, this much of kVA is required to get maximum efficiency, which is nothing but what? E2I2, right? Then we have to calculate the value of x, which is equals to what? Square root of pi by PCU. What is the fraction of x? Which is equals to 1 by root 5, which is nothing but 1 by root 5, which is equals to 0.4472. So x into E2I2 cos phi 2 by x into E2I2 cos phi 2 plus s square into PCU and pi. Given that cos phi 2 is what? This is x. Given cos phi 2 is what? 0.8 lagging, and given that the pi 120, PCU, pi should be 120, PCU 600, and kVA should be equals to what? 21.467. That's it. Very simple formula. Then substitute this all data into this equation. We are going to get the maximum efficiency. So if x is what? 0.4472 into, this is what? 21.467 into power factor is what? 0.8, right? 0.4472 into 21.467 into 0.8 into s square is what? 0.4472 whole square into copper loss content is 600 plus iron loss component is 120. So from this we are going to get the efficiency maximum as 98.62%. So like this you have to calculate the maximum efficiency. Next, calculate the regulation of a transformer in which ohmic drop is 1%, that is percentage R drop should be equals to what? 1%, and reactance drop is what? Percentage X drop should be equals to what? 5% of the voltage at the following power factors: 0.8 lagging, 0.8 leading, UPF. Simple formula and simple problem. First we have to write the percentage voltage regulation should be equals to what? Percentage R into cos phi 2 plus or minus percentage X sin phi 2. So what is the first bit? Percentage voltage regulation at 0.8 lagging, right? That is, what is the answer for this? Percentage voltage regulation at 0.8 lagging. This is cos phi 2 is what? 0.8, sin phi 2 is nothing but 0.6. So percentage R cos phi 2 plus y plus, because lagging, percentage X sin phi 2. Percentage R is what? 1 into, what is the value of cos phi 2? 0.8 plus percentage X is given as 5 into sin phi 2 is what? If it is 0.8 for cos phi 2, 0.6 for sin phi 2, since sin phi 2 should be equal to square root of 1 minus cos phi 2 whole square, you will get 0.6. Okay, what is the answer? 0.8 plus 3, that is the, what is the answer? 3.8, right? The answer is 3.8. the percentage voltage regulation under lagging condition, right? We have positive value, right? Next, B. Percentage voltage regulation at 0.8 leading. What is the formula for the percentage voltage regulation, which is equals to percentage R into cos phi 2 minus percentage X sin phi 2. Why it is minus? For leading condition, minus sign is there, that is 1 into 0.8 minus 5, what is the answer? 5, right, into this is 0.6, so 0.8 minus 3, the answer is what? Minus 2.2%. We all know that negative voltage regulation is possible under leading condition. Satisfied? Next, percentage voltage regulation at UPF. So we all know that what is the percentage voltage regulation at UPF? Only percentage of simple at UPF phase angle, which is equals to what? 0 only. That's why there is no sine term. Therefore, what is the R? 1% only. So at UPF we have 1% of voltage regulation. Under leading condition we have negative voltage regulation. Under maximum condition we have under lagging load we have maximum voltage regulation, sorry, positive voltage regulation. So this is the problem based on the voltage regulation. Next one, a 20 kVA 50 Hz 2200 by 220 volt single phase transformer has the following test results. From OC test, these are the results: rated voltage, no load current, iron loss component, and rated voltage, 5% of rated voltage and rated current, and copper loss content. Determine the regulation at 0.8 power factor lagging and at full load. What is the power factor on short circuited condition? So first we have to calculate test results. Then OC is given, S is determine the regulation at 0.8 power factor lagging at full load. What is the power factor on short circuited? Cos phi should be equals to R by Z. Therefore, referred to primary, I have to calculate. So cos phi should be equals to R01 by Z01. So to calculate this power factor, cos phi SC should be equals to what? R, which is equals to R02 by, but here I am going to consider this, right, referred to primary. So we have to calculate R01, later we have to calculate Z01. Okay. So we all know that Z01 should be equals to what? VSC by ISC. What is VSC? VSC is what? 86 volts. ISC is what? 10.5, right? So from this, Z01 is what? 8.19 ohms. Okay. And then R01 we have to calculate. We all know that wattmeter readings by short circuit current square, which is equals to, under short circuit condition, WSC is nothing but what? 360 watts by ISC is what? 10.5 whole square, which is equals to what? 3.27 ohms. Okay. So we have power factor. Then before that, first we have to calculate the regulation at 0.8 power factor. So for that we have to calculate X01, that is square root of Z01 whole square minus R01 whole square. Very simple problem, just you have to go through the concept. So from this you will get the value of Z01, X01 as 7.51 ohms. Then I1, to calculate regulation, first we need to calculate I1, which is equals to kVA rating by what is E1, which is equals to 20 into 10 cube by E1 is what? 2200. What is the answer now? This is 9.09 amperes. Now we have all the data. I1 R01 cos phi 2 plus I1 X01 sin phi 2, right? Percentage voltage regulation, which is equals to I1 R01 cos phi plus I1 X01 sin phi by, with respect to primary, that's why V1, okay, into 100. I1 is what? 9.09 into R01 is what? 3.27 into 0.8 plus 9.09 into X01 is what? 7.51 into 0.6 by P1 is what? Which is equals to E1 into 100. We are going to get 2.94%. The percentage voltage regulation is what? 2.94. Just you have to calculate I1, R01, I1, X01 and Z01, and therefore cos phi s is what? R01 by Z01, which is equals to 3.27 by 8.19, which is equals to 0.4 lagging. Simple. We have to calculate the cos phi sc, that is R0 by R by Z. We have Z and R. To calculate voltage regulation we need X, that's why we have calculated X from this R and Z. To calculate regulation we need I1 with respect to primary, that's why 1 I1 X01 R01 Z01. Then this is the formula to calculate voltage regulation referred to primary, or you can calculate it from referred to secondary. You will get the same answer. Okay, R02 Z02 X02 and I2 in place of E2 you have to put E2, that is you will get I2 R02 cos phi plus I2 X02 sin phi by E2. From this also we will get same answer. Okay, next problem. The maximum efficiency of 500 kVA 3300 by 500 volts 58 single phase transformer is 97%. Occurs at 3/4 of full load and the power factor is what? UPF. If the impedance is 10%, calculate the regulation at full load, power factor 0.8 lagging. Okay, so at 3/4 full load and UPF power factor, output should be equals to what? 500, right? Which is equals to 500 into E2 I2, right? E2 I2, let us take before that X into E2 I2, right? Into cos phi 2, X into E2 I2 cos phi 2, output by input, right? What is X? 3/4. E2 I2 is what? 500 into power factor is what? 1, which is equals to what? 375 kilowatts. Therefore for maximum efficiency, which is what? 97%, which is equals to 0.97. Therefore input should be equals to what? Output by efficiency. What is output? 375 by 0.97. What is the input? 386.6 kilowatts. Clear? This is input, this is output, this is the efficiency. So this loss is equally divided between iron and copper losses. So total losses we have to calculate now. Total loss should be equals to input minus output, right? Which is equals to input is what? 386.6 minus output is what? 375. What is the answer? 11.6 kilowatts. So here given the condition is what? Maximum efficiency. Under maximum efficiency we all know that at efficiency maximum, what is the condition? Iron loss content should be equals to copper loss content, right? And UPF power factor. Under maximum condition only, what is the relation? Iron loss component should be equals to copper loss component and we have unity power factor. So this is the total copper loss content, total loss component in the transformer. So equally divided. Therefore you have to write that point. Therefore at maximum efficiency, total loss in the transformer is equally divided. What is the reason? Since at maximum efficiency Pi should be equals to PCU. Therefore, that is S square of PCU should be equals to Pi, right? S square of PCU should be equals to PCU. That is 3 by 4 whole square of PCU, which is equals to Pi, which is equals to P total by 2. What is P total? 11.6 by 2, which is equals to what? 5.8 kilowatts. Okay. Therefore, from this PCU should be equals to what? PC should be equals to 16 by 9 into 5.8, that is 10.3 kilowatts, and Pi should be equals to what? 5.8 kilowatts. So we have copper loss content, iron loss content, right? And then we have to calculate, if the impedance is 10%, calculate the regulation at full load. At full load, I2R02 into cos phi 2 plus I2X02 sin phi 2. Okay. So we have to get percentage resistance. Percentage resistance, which is equals to I2R02 by V2 or E2 into 100, which is equals to I2 square R02 into E2 I2, which is equals to E2. Let us multiply I2 by I2, which is equals to I2 square R02 is nothing but what? Copper losses, right? By this is E2 I2 into 100. What is the copper loss content? 10.3. This is 500 into 100, which is equals to what? 2.06%. That is percentage R should be equals to what? 2.06%. Then given percentage impedance is what? 10%. Therefore, from this two, percentage reactance should be equals to square root of percentage Z whole square minus percentage R whole square, which is equals to 9.786%, right? Therefore, finally percentage regulation we have to calculate, equals to I2R02 cos phi 2 plus I2X02 sin phi. Why it is plus? Because he wants the data under lagging condition. E2 into 100, which is equals to percentage R cos phi 2 plus percentage X sin phi 2, right? What is the value of percentage R? 2.06 into cos phi 2 is what? Given that 0.8. Percentage X is what? 9.786 into 0.6. What is the answer? 7.52%. So like that you have to calculate the percentage voltage regulation with the copper loss content. So this is a very important problem. Just go through this problem once. So all of you go through this 15 problems once again. So all of you go through this 15 problems once again with clear cut concept. Thank you all of you.